That's not what you are here for. We have this new simulation in use. We have this new simulation, new simulation, new simulation. I'll share the link with you. It's not published on the website yet, but if you're watching the live streams, you'll get it first. It's to do with K-theory. K-theory, everyone loves a good piece of maths, but this one actually doesn't have any questions on it. That's great, isn't it? No equations is awesome. So I'll try putting it in full screen. We have a demo mode running. I mean, you can interact with it yourself. And the demo should start 10 seconds after the user is not interacting with the page. So it's already up and running. It should run in a loop. We gave the code to Gemini 2.5 Pro. And we'll listen to 5 minutes of overview. And we'll go from there.
Yoshik, my friend, you must see this. It's a simulation of K-theory.
K-theory? Sounds like a conspiracy theory involving breakfast cereals. You won't believe what they're really putting in your Cheerios. It's the letter K.
Not quite. It's a mathematical tool to classify complex systems. Think of it as a way to find the hidden patterns in the chaos of life. The website calls it an interactive analogy.
The chaos of life? You mean like when you're trying to fold a fitted sheet and you suddenly question all your life choices?
Exactly. Or on a grander scale, think about things like ecological systems or even the stock market. It's all a beautiful mess. K-theory is about understanding the topological charge of that mess.
Topological charge? Is that what I get when I plug my toaster in with wet hands?
Close. Think of it like this. You have a field of arrows all pointing in different directions. A vortex is a swirl, a point where the arrows spin around. K-theory counts the net number of these swirls. A vortex is +1, an anti-vortex is -1.
So if my life is spinning out of control in a counterclockwise direction, that's a +1? And if it's spinning clockwise, it's a -1?
You've got it. And here's the cool part. If you have a vortex and an anti-vortex, they cancel each other out. Your K-class, the total score, becomes 0. The system looks complicated, but its net charge is trivial.
Ah, the principle of canceling out my bad decisions with equally bad but opposite decisions. I'm familiar with this. Like eating a whole pizza, but then having a diet soda. The K-class of my stomach is 0.
That's a creative application. But you've grasped the core idea of K-theory. Vortex plus anti-vortex equals trivial. The interactive simulation on the website lets you add these vortices and anti-vortices to see how the K-class changes.
So K-theory is the mathematics of it all evens out in the end. Sounds suspiciously optimistic for a data scientist.
It's not about optimism, it's about structure. The K-class is a topological invariant. That means it's robust. You can't change it with small nudges. You can comb the field all you want, But the only way to change the K-class is to add or remove a whole vortex.
So no amount of rearranging the deck chairs on the Titanic will change the fact that you've hit an iceberg. You need another iceberg to cancel it out. Got it.
Or, more practically, think about data. The website mentions using this for biomedical data analysis. Imagine you have a ton of data from a tumor. You could use these ideas to find the significant, robust structures in that data, the vortices that tell you something important is happening.
So K-theory helps you find the tumultuous swirls in a sea of boring data points. I like that. Does it have any other fun applications?
Well, it has applications in string theory.
String theory. The theory that says the universe is made of tiny vibrating strings. So K-theory is how we know if the universe's strings are tangled up in a cosmic knot.
In a way, yes. It helps classify the complex spaces that string theory predicts. The website even talks about extending the analogy to higher dimensions and using it to visualize things we can't see.
Higher dimensions. So you're saying there's a dimension where I can eat all the pizza I want, and the K-class of my health is always +1. Sign me up.
I'm not sure that's one of the dimensions K-theory has discovered, but it does show us that even in the most chaotic-looking systems, there are fundamental, unchanging properties.
So K-theory is like a comedian's punchline. You have all this complicated setup, all these details that seem random, but then there's one simple, elegant twist that makes it all make sense.
I've never thought of it that way, but that's a perfect analogy. It's the punchline of the universe.
And the universe, my friend, is a very, very weird joke. I'm glad we have mathematicians like you to figure out why it's funny. Now, about that breakfast cereal conspiracy.
Yeah, that was pretty good. That was Gemini. You can check the tool yourself. You can interact with it as well, or run pre-simulated stuff. Because apparently K-tier is very hard to visualize while we're giving it a crack. Everything we do, by the way, is available on BioniChaos.com. Go check out the website. Let us know what you think. Let me know if you have any questions about any of the tools or any suggestions as to how we could improve them. Will be more than welcome as well. Do let me know if you use a K-theory, or if you're a mathematician, if you can actually check that the code is correct for this. It doesn't look like the magnet simulation we have. Yeah, this one here, I haven't looked at it for a while. Can add up to 4 magnets in this one. You can move them around, rotate them, and see the magnetic fields. Hey, can you give one sentence on each web application?
Absolutely. One K-theory, an interactive demo that visualizes topological K-theory using vortices and vector fields, illustrating topological invariance. Two, an interactive magnet simulation that lets you add, move, and rotate magnets, visualizing magnetic fields and forces in real time.
Okay, and how they related to one another?
They both serve as educational tools that visualize complex abstract concepts in a tangible way. The K-theory demo illustrates topological invariance, while the magnet simulation visualizes physical fields and forces. Both rely on intuitive, interactive visualizations to help users grasp abstract mathematical or physical principles.
But how are magnetic fields actually relevant to the dynamic analogy in the K-theory web application?
That's a really interesting question. In a direct sense, the magnetic field in the magnet simulation and the topological concepts in the K-theory demo are quite different in their physical and mathematical bases. However, both applications illustrate the idea of invariance and stability under certain transformations. In the K-theory demo, the K-class remains unchanged unless you add or remove a vortex, similar to how certain topological features remain stable despite local changes. The magnet simulation shows how the overall magnetic field remains consistent unless you change the sources. So both highlight the concept that certain global properties are invariant under local changes, which is a nice conceptual link. Absolutely. Think of it this way. The K-theory demo shows how some topological features are like secret invariants that don't change no matter how much you twist or turn the field, kind of like how a magnet's overall magnetic field stays consistent no matter how you move it around. So both demos are all about how certain global properties hold steady, even if you fiddle with the details. If that sounds cool to you, definitely check out both tools and let me know what you think. Of course. You can check out the K-theory demo at BioniChaos.com. K-theory. And the magnet simulation at BioniChaos.com. Magnets. Go explore them and feel free to share your thoughts. Great question. The magnet simulation can actually be pretty relevant to biomedical data science because the principles of magnetic fields are at the heart of technologies like MRI, which is a cornerstone in medical imaging. Understanding how magnetic fields interact, how they combine, and how they produce forces is super useful for visualizing and interpreting biomedical data. So the simulation gives a hands-on way to understand these concepts, which can definitely help when dealing with complex medical imaging data. It's a neat connection. The K-theory demo is a bit more abstract, but it's still relevant in a biomedical context, especially in areas like computational biology and the study of complex biological systems. The idea of topological invariance can be applied to understanding the stability of certain biological structures or networks, kind of like how certain properties of proteins or cellular structures remain unchanged despite various transformations. So in a sense, it helps in understanding the underlying stability of complex systems, which is super handy in biomedical data science. It's a cool out-of-the-box connection.
Yeah, okay, that was ChatGPT assuming 5, version 5 or another one. Well, that's the voice model, so it will be different model altogether, potentially. Everything we do is available on BioniChaos.com. Go check out the website. Let us know what you think.
I see a web page on BionicChaos.com. It lists several simulations and image viewers, including a Hodgkin-Huxley action potential model, an HRF image database viewer, an interactive magnet simulation, a guide on predictability versus creativity in AI, an advanced hair cell simulation, and an interactive physiological signal visualization. Did you want me to elaborate on any of these? Certainly. The web page now shows an interactive physiological signal visualization that looks at cognitive load and emotional arousal on things like ECG and EDA signals. Below that, there's an interactive TMS simulation to visualize transcranial magnetic stimulation on the brain. You can also find an action potential architect, an interactive neuron simulation. Lastly, there's an interactive spectrogram generator for visualizing various signals, like EEG and EMG. I hope this helps with your development. Let me know if you want any further explanation. This page is an ultrasound simulation, a medical exploration. It shows a kidney and a cyst/fluid on the screen with emit pulse, audio off, and play demo buttons at the bottom. To make it even better, you could add options to adjust parameters for the ultrasound pulse, like frequency or depth, or include controls to change the type of tissue being scanned beyond a kidney and a cyst. I also see the URL is listed above, so I encourage viewers to check it out for themselves at bionichaos.com/ultrasound. This simulation is a really great way to learn about ultrasound. Hey everyone, checking in with this ultrasound simulation we've been working on. Right now, it's showing a kidney and a cyst or fluid on the screen, and you can emit a pulse, turn audio off, or play a demo. What kind of other medical explorations do you think would be cool to simulate here? Maybe different tissues or different parts of the body? And how can we make the visuals and the pulse itself look more realistic? Any thoughts on making it more engaging for everyone watching? Let me know in the comments. If you want to play around with this simulation yourself, head over to bionichaos.com/ultrasound and give it a try. I'd be interested to see what you discover. Sure thing. So let's talk visuals. To make the simulation look more like a real ultrasound, we could add some grayscale imaging. That fuzzy black and white look is classic for ultrasounds. Also, instead of just the simple yellow dot reflecting, we could make the sound waves emanate across the image from the probe and then return, maybe with little visual indicators of where the echoes are coming from. What do you think about that? Anything jump out to you? You're absolutely right. The idea is to reproduce the image of the sample based on the emitted pulse and the reflected echoes. We could create a separate area on the screen, maybe off to the side, that fills in real time as the pulse travels and reflects back. Think of it as a live image being built, showing different brightness levels based on how quickly the sound waves return. This way, viewers could follow the journey of the pulse and see how it creates the final image. What kind of visual style do you think would make this clearest? Any specific examples you have in mind? So we could have the main simulation area remain in the simple colors it is now, but then create a separate results panel, maybe a square or rectangle on the side, that displays the ultrasound image in grayscale. As the virtual probe moves across the kidney, the cyst, and the bone in the simulation, the corresponding parts in the results panel would fill in with different shades of gray. The bone, which reflects sound the most, might be white, while the cyst, with its fluid, would be darker. Would you like to explore the different grayscale values for the different elements? To make it clearer, let's picture a second image display on the screen, maybe on the right side. This display would be where the ultrasound image is actually created. As the sound waves reflect from the different parts of the simulation, the kidney, the cyst, the bone, those echoes would be used to draw the image in this new display. Different shades of gray would represent how strong the echoes are. Does that make more sense as a way to visualize the process? Yes, that yellow bit is likely meant to represent a kidney stone. Since stones are very hard and dense, they reflect sound waves very well. So in the reproduced image, it would appear as a very bright white area, and it would likely cast a shadow behind it, meaning the area behind the stone would be much darker than the surrounding tissue, because sound waves can't pass through it easily. Does that make sense in terms of the visual representation? Certainly. Here's a prompt you can give the developer. Enhance the ultrasound simulation to include grayscale imaging for the reproduced image. Implement a visual representation of the sound pulse emission and reflection, displaying the echoes with varying brightness levels. Specifically, ensure that the bone and the kidney stone appear as very bright white areas with a noticeable darker shadow behind the stone. Different elements, like the kidney and the cyst, should have distinct grayscale values to represent their different densities. Does that cover everything you had in mind?
Certainly. You can suggest that the developer assign different grayscale values to the various elements, like the kidney, the cyst fluid, and the bone, based on their expected echogenicity. For the sound pulse visualization, they could use a moving line or pattern to represent the pulse traveling through the simulation, and then brief flashes or dots appearing to show the echoes returning to the probe. The timing of these reflections should correspond to the distance of the object from the probe, with closer objects producing quicker reflections. They could use a separate image element for the grayscale output, updating the pixels based on the brightness values and the timing of the reflections. Would you like further details on how to handle the grayscale values?
So trying to improve this web application, it's ultrasound simulation. Obviously, the missing bit is the reconstructed image. So I have a grayscale inset somewhere to show how the image is being reconstructed from the emitted pulses. From the emitted pulses. I'm using Gemini 2.5 Pro for this. You can check out the current version, play around with it, see how it works. You can move the probe, emit pulse. There should be a keyboard shortcut. Yeah, you can use the arrow keys. And I need to stop the demo first. The demo idea should stop by itself. Keyboard. You can move it with group. Should be a keyboard shortcut for actually generating a pulse. But let's see. To fix a few styling things on the page as well. A few styling things on the page. But supposedly we have a better code. We will run it locally. 769 lines. So test it locally to know when the image is reproduced. And just grayed out. By the way, all this focus is on the pages you make. So just grayed out the thing. And not sure what did it do. It's, by the way, not being reflected from the cyst. I didn't quite get it. Hey, I didn't quite get what are we trying to do. I thought there will be another inset with the reproduced image from the scan, but it seems like the whole thing was just grayed out. Is it meant to be gradually returned to its original colors or something as the scanning progresses? Hey, can you also explain now? The pulse is just going through the cyst. It's not seeming to detect it. Can you explain that bit? A clear image doesn't seem to do anything at the moment, and there are no error messages, so not sure what's up. Another small thing, if we're already changing the code, if you because you're gonna regenerate the whole code, is the demo should just start by itself if the user is not interacting with the page for more than 10 seconds, and the demo mode should also stop if the user clicks on something. So ignoring hover over with the mouse, but the actual click on the page should stop the demo, and the demo should resume if the user is not interacting with the page over 10 seconds. And let's see. That's the original one. The new thing doesn't seem to be a major improvement. Wait, so, oops, to stop demo. Yes, probably mid pulse. Being returned from the cyst as well. So it also will depend on the settings of the ultrasound device, if it detects certain things or not. I would believe we could explore that one as well. Okay, so we have a beta version, play mode, play demo, sorry. Oh, yeah, the play demo should not stop. Okay, I get the, yeah, that's very nice. So we'll have, you expect this to have errors. Can't move the probe. Yeah, can we bring all the previous functionality back? We should be able to move the probe and mid pulse manually. The play demo, we need to fix the play demo. Currently, when I click on it, it stops immediately. Well, there's a conflict, there's a bug there. Because we said we need to make sure it starts automatically if the user is not interacting with the page for more than 10 seconds, and if they do interact by clicking, so ignoring hovering over the page, the demo mode should stop. Yeah, we need to keep the audio there, clearing image. Well, we can't test it at the moment, so we need to regenerate the whole code for it to work, bring back all the previous functionality. If you can. At least it's generating code real fast. That's very nice. It's Gemini. This video is brought to you by Gemini 2.5 Pro. And everything is available on BioniChaos.com. Go check out their website, provide your feedback. We'll be using it for future prompts. And don't forget to subscribe to the YouTube channel so you don't miss the live streams. And go check out the many alpha simulations we have on the site. And we should have a new code by now. Yes, we do. Yes, we do. And we expect it to be. It's too short. Getting rid of stuff. I don't like it. What on earth? Copy paste properly? It's hallucinating on us. Hallucinating on us. Oh, what? It's actually working. So it's generating these pulses and reconstructing the image. Yeah, that's the base plate for the sample, I would imagine. And it's having trouble there. That meant to be the cyst in theory, and it cannot find the cyst slash fluid. I do like it. Oh, I'm able to emit pulse. So if we clear the image, yeah, just going through the cyst, if we have it here visible, it will bounce back and generate something there. This is going to become stronger and stronger. Kinda is. It's missing the kidney stone, so it's finding the kidney, but the kidney stone meant to be there is being missed. So, so in theory, we should be able to adjust the settings of the ultrasound. Does anyone know how ultrasound works? Anyone? Anyone? I do like it. I do like it very much. And now it's been like a sound array as opposed to what we had before as a single thing. I don't know what they're called. A single thing. Can we make sure the description at the bottom of the page is updated based on the changes to the code? Also, yeah, so the play demo works fine. For some reason the audio is not working. Manual emit pulse is working okay. Clearing image works. Yeah, it does work. Now we need to explain either future directions at the bottom of the page. So we need an overview. We need the technical details. We need how to use section. We need future directions. Now we need to explain how in this case, for example, how do we tune the parameters of the ultrasound scanner? How do we change the parameters to find the kidney stone or the cyst slash fluid? So in theory we should be able to change the parameters and then it will be tuned for one or the other. And the bone as well. So currently I would imagine it's finding only the bone and the kidney. So can you explain that? We need it in the explanation below the page. We'll generate another podcast out of this. I've been talking for too long. But it is much better than what we had before. Thank you very much. Thank you, Gemini 2.5 Pro. okay, well, want to change the sound based on what the emitted pulse is detecting, so it's not just the same sound all the time. There's some sort of weird feedback, has some sort of weird distortion to it, but it is better. And by the way, that's wrong. I thought that's the base plate of where the so that's the bone, because that's assuming live human something. I thought it's just a kidney outside the body or something, but no. Anyway, yeah, that's the bone at the bottom. So currently it's only finding the kidney and the bone. It's not finding the kidney stone and the cyst, the fluid cyst. They also mark them up. But it is much better than what we had before.
Yojic, I've been watching you mess with that ultrasound simulation for an hour. You haven't blinked. Are you okay?
Okay, Misha, I am transcendent. I have seen the inner world. I have orally experienced the silent cry of a kidney stone. I am pretty sure I'm now qualified to tell a panda it's pregnant.
Please don't. But I'm glad you like it. It was quite an iterative process to get here, wasn't it? Thinking back on our chat.
Iterative process is a very data scientist way of saying it was a hilarious mess at first. Remember version 1? The one where I clicked scan and the whole screen just went gray, like it had seen a ghost? I thought my monitor was giving up on life.
That was the B mode overlay. Logically, it made sense to render the grayscale image on top of the anatomy. In practice, not so intuitive. Your feedback about needing an inset was the key. Separating the physics model from the clinical output made all the difference.
It was the difference between abstract art and an actual instruction manual. But then came the demo button with the existential crisis. I'd click play demo and it would immediately stop. It was like a teenager I'd asked to do a chore. I'm doing it. Okay, I'm done.
A classic event propagation conflict. The click to start the demo was also being registered as a user interaction to stop the demo. It was fighting itself.
I know the feeling. My favorite part, though, was our conversation about tuning the machine. I genuinely thought you have to turn some secret dial to make the cyst invisible so you could find the stone.
And that's the beautiful core of it. You don't tune things out. You learn to read the signals. It's all about echogenicity, the different ways materials talk back to you.
Right. I finally got it. The kidney stone is a heckler in the front row, loud, obnoxious, and reflects everything you say right back at you. The bone is the same, but it's a huge bouncer who casts a big shadow so you can't see the guy behind him.
A perfect analogy. And the cyst?
The cyst is a mime. It's in the room, you know it's there, but it contributes absolutely nothing to the conversation. Just lets everything pass right through. Total silence.
I'm going to use that. But the real breakthrough was your last question, the one about the sound.
Ah, the theremin of internal organs. That was the game changer. It's one thing to see the bright white dot, but it's another to hear it. That loud, high-pitched ping for the stone, and the deep, loud thump for the bone. You can literally close your eyes and find the pathology.
It's a direct sonification of the data stream. We mapped echo intensity to volume and reflection depth to pitch. It's a more visceral way to understand the data. You can hear the acoustic shadow because the pings just stop.
So, what's next in the future directions? Are we adding a Space Invaders mode where you have to shoot the kidney stones?
Tempting, but probably Doppler mode first, simulating blood flow. You not only see the red and blue flashes, but hear that classic whoosh whoosh sound.
Amazing! So we're building a tool that lets you play a video game inside your own body with a custom soundtrack composed by your own anatomy.
That's one way to put it. It started as a simple request to fix a display and ended up as a multi-sensory diagnostic tool.
Well, that's how all the best things happen, right? You start with a problem, add a little logic, a dose of confusion, and a smart comedian to ask the obvious questions.
I'll concede the last part was surprisingly useful.
I'll send you my rates. They're very reasonable.
we do is available on BioniChaos.com. Go check the website and provide your feedback. We'll be using it as future prompts.